The rest of today is going to be a bit of a grind. The first section of this course has a lot of definitions, basically, and pretty basic concepts that we'll be using just as our tools to be able to solve problems and learn new types of analysis for fluids. So today is going to be kind of like the rest of it is going to be kind of like a PowerPoint presentation. I promise to not make the rest of the slides for this course just me reading slides off. I know you guys can read. But for this part, just to try and get through it somewhat quickly and efficiently, if you go through this section and you read this section of the textbook, you should have a pretty good grasp on everything to set you up well for the rest of the course. So just in this last half of today, we're going to go through basically all of chapter 1 relatively quickly. That's just dimensions and units, talking about what's the difference between primary and secondary units and the importance of dimensional homogeneity or dimensional consistency. And then we'll talk about fluid properties. So there's extensive versus intensive properties, pressure and stress, the viscosity, surface tension, and then finally the ideal gas law. All right, so in order to talk about quantitatively properties, the condition of a fluid, or what have you, we need to define basically two things. One of them is dimension, and the other is unit. And dimension and units are particularly important for fluid mechanics because there is an entire branch of fluid mechanics that is dimensional analysis, closely tied to experimental methods. So dimension is defined as the measure by which a physical variable is expressed quantitatively. So for example, what is the measure that we use to quantify the height of a fluid container? The answer to that would be length. And there are four, depending on the system you use, four fundamental dimensions. You'll see that in the next slide, but they're mass, length, time, and temperature. And then all of those dimensions have an associated unit, and then any other unit can be derived from those base units or base dimensions. So if the dimension is length, units that can correspond with lengths, if we use the SI system, would be a meter. So what is the unit of the dimension length in the metric SI system? The answer to that is meter. So I'm going to try and follow this as much as possible, but I'm going to use curly brackets to group dimensions and square brackets to group units. So dimensions will be these types of parentheses. Can't draw them very well. And then if I see square brackets, that will typically denote units. So the big difference between units and dimensions are basically whatever measure it is describing a physical variable, and the unit is the particular system that you're using to describe that unit of measure. So a dimension would be length, and a unit would be meter. A dimension could be mass, and a unit could be kilogram, and so on. So if we use the SI system or the British gravitational unit system, there's four primary dimensions, and then each unit system has their associated units with a primary dimension. So mass and SI, dealing mostly with SI, maybe some British units as well, but mass is kilograms, length is meters, time is seconds, and temperature is in kelvins. And then for British units, mass is a slug, length is foot, time is seconds, and temperature is degree Rankine. And then at the right-hand side, there's just a conversion factor, so you can convert between these two units. All other properties are derived from these dimensions. Hence, we call these primary dimensions. So for an example, derive the units for force in terms of primary units. So let's choose our SI system. So in SI. Force is in the units of newtons. How can we write this in terms of our primary dimension, or primary units?
I guess it's mass
times kilograms meters per second squared. Yes, if we think of force is equal to mass times acceleration, mass has the units mass, acceleration has the units of length per time squared. Meters per second squared is length time squared. So we would write our base units as m mass L length times t to the minus 2, or to the power of minus 2. Or you could write this as ml t squared. This is more conventional. Good. These slides will be on Brightspace after the lecture. What I'm going to do in the future is I'm going to actually post them ahead of time. So if you want to have a copy with you to follow through, then that's completely fine. So here's a list of some secondary dimensions. There's many more than just this, but these are a lot of the ones that are applicable to what we're going to see in this course. Like area, volume, velocity, acceleration, pressure, and stress are the same dimensions. Angular velocity, heat, energy, work, power, density, viscosity, and specific heat. And then you can see the units for SI and BG systems, and then there's conversion factors as well. So this would be a good reference. So in other unit systems, some systems require what's called a proportionality constant to ensure dimensional consistency. And we haven't quite dimensional consistency yet, but we will get into that. So for example, if you consider the English system, it has units of pound force, pound mass, foot, second, and so if we rewrite Newton's second law, force is equal to mass times acceleration divided by GC, where GC is equal to 32.174 pound mass per slug. So this is an example of a proportionality constant, and even though it is a constant, it has dimensions. So it has a value and dimensions. We'll try to stay clear of these, but you do need to note that depending on the system that you are using, sometimes there will be these proportionality constants involved to ensure we have something called dimensional consistency or dimensional homogeneity. We can also introduce prefixes. So kilogram is actually the base unit for that would be gram, but we've decided that kilogram is our base unit because it's more closely related to things that we would deal with on an everyday basis. Speaking in terms of how much things weigh in terms of grams, the numbers just get too huge sometimes. So kilo is the prefix, which just means 10 to the power of 3 or 1,000. So kilogram is 1,000 grams. And then common ones that we use most of the time tend to fit in this category here, where you might see giga, or even with computation now in memory, we'd see tera, so terabytes, gigabytes, megabytes, kilobytes. These are the realm that we see most oftenly used. We don't use these two very often. I won't put an X, they're not wrong, they're just not too oftenly used. And then we also see things in units of length, where we might get down to decimeters, centimeters, millimeters, micrometers, and even nanometers, which would get us down to basically the atomic scale. So atom this big somewhere here, or interatomic spacing for liquids would be around that space. So this can often just sometimes make it more convenient. So very simple. If you wanted to write 114 million million pascals, we can use megapascals. So if a megapascal represents 1 million pascals, this would just be equal to 114 megapascals. And then likewise, if we wanted to write 0.0000000 seconds in terms of a unit that might be easier to write or comprehend, we can write it in nanoseconds, and nanoseconds is 10 to the minus 9, or 1 billionth of a second. So this number here is 3 billionths of a second, or 3 nanoseconds. So what is dimensional consistency and why is it important? Dimensional consistency or homogeneity, essentially ensuring that our equations will give us something meaningful and realistic. And in order to have this, we need to make sure of 3 rules. First one is always have one unit system in your calculations. So we cannot add slugs and kilograms together. We have to add kilograms and kilograms, or slugs and slugs. So we need to convert one to the other. If we add 1 slug to 1 kilogram, we get some sort of nonsensical answer. It doesn't really provide us any value. So we have to ensure our units are consistent in that we use the same unit system and they are the same unit prefixes. So 2, always use the same unit prefixes. So we have the same system now. We have megapascals and pascals. They're both units of pascals, but we can't add 0.1 MPa to 10,000 PA. We'd have to convert them all to the same power of 10. So we can add MPa and MPa, or we can add pascals and pascals, but we can't add to each other without converting. And then lastly, this is probably the most important one, where maybe option 1 and 2 are where mistakes come in a lot of times. But number 3 is maybe a little less obvious when we first look at this, but it's important to make sure that we put extra effort into ensuring that we always make sure our equations are dimensionally consistent, which means that every single term in the equation has the same dimensions. So the first 2 deal with units and making sure we have the same units. The third rule applies to dimensions, which we could say is units as well. But what we mean by dimensions is, for example, down here, force times velocity, or force plus velocity. The units of force we said above are mass times length times time to the power of minus 2. The velocity is a unit of length times a unit of time to the power of minus 1. So these have different dimensions. We add those together. They need to be the same. So you cannot add force and velocity. They're just inconsistent. And I mean, you can add those terms, but they're going to give you something that's nonsensical. It's not going to be physical or realistic or really make any sense. So an example where you might be asked to show this principle. Let's look at an equation that we're going to become quite familiar with, the Bernoulli equation. And this question is basically show that the Bernoulli equation is dimensionally consistent, which just means that show that the base dimensions, if we write each of these in terms of base dimensions, that they are the same for each term in this equation. So if we write out the base dimensions for pressure, P, so this is pressure, rho is density, V is velocity, that's also rho, G is acceleration of gravity, C is our height. So if we rewrite this equation, those three terms, the first term is pressure, and the base units for that are mass times length to the -1 times time to the -2. And each terms in the, or each of those variables in the second term, we have density, which is mass per unit volume. So we have mass times length to the -3 times our velocity squared. So we have length times time to the -1 all times to the power of 2. And then our third term, we have density. So that's mass times length to the -3 again. And this is going to be times acceleration due to gravity. So our base units for acceleration are length times time to the power of -2. And then our last dimension is height, which is the dimension of length. So we have to show that these are all the same. Well, if we simplify this term, we have a unit of mass. We have length to the power of -3 times length to the power of 2. So we have length to the power of -1. And then we have time to the power of -1 squared, so time to the power of -2. So that's the same as the first term. So that one's good. And what about our second term? We have mass. We have length to the power of -3 times length. So that's just length to the power of -1. And then we have time to the power of -2. So we have mass, length to -1, time to -2. That's correct. So Bernoulli's equation is dimensionally consistent because every single one of those terms in that equation has the same base dimension. So we would call this dimensionally consistent. So we just spent a few slides talking about how all equations need to be dimensionally consistent. And now I'm going to tell you that that's not actually true because a lot of work in experimental work specifically, trying to find equations to describe behavior of materials. And these equations a lot of time are just based off of numerical data or data that we collect. And if we have an expression or an equation that's based on data and not on physical fundamentals of material behavior, we call these empirical formulas, or sometimes semi-empirical formulas if there's some gray area between. And sometimes these formulas break the rules of dimensional consistency. So if we look at this equation at first, we have Q, which is our volume flow rate. So volume flow rate would be a volume per unit time. So we have a volume length cubed times t to the -1. And we're saying that is equal to this dimension here, which is our change in pressure. And SG is our specific gravity. So our units for our change in pressure over specific gravity would be, let me write this over here. Delta P is our mass times length to the -1 times the -2. That's pressure, that's the same as before, divided by our specific gravity, which is mass to the power of, made a mistake in this have a 1/2. Mass to the power of, sorry, specific gravity has dimensions of 1. How many dimensions? So if there's no dimensions, we'll just write 1. So this total dimension is all to the power of 1/2. So if we were to write this out, we would get mass to the 1/2, length to the 1/2 times time to the -1. So this is not equal. And the value CV here is a valve flow coefficient. So that coefficient is just a fitting parameter. It would be something that would be representative of a specific case to make sure that this expression works and fits the data, whatever it was developed for. So what we do to try to get over this is we would give this coefficient a dimension so that the equation becomes consistent. And so the dimension for this example for CV would be length to the power of 1/2 times mass to the power of -1/2. So if those are the dimensions, and I should write them consistently, those would be the dimensions of our valve flow coefficient so that our equation is now dimensionally consistent. So there will be times when you see equations like this that don't appear to be dimensionally consistent because CV might just be given as a constant and doesn't actually have units. There are units associated with it, they're just not always presented. All right, perform a dimensional analysis on a formula for the mean free path of a gas, and what must the dimension be for a constant 1.26 to maintain dimensional homogeneity. So in this case, we have a constant, but it's actually a number, it's not a variable, and that number is 1.26. So if our length, mean free path has units dimensions of length, our viscosity, mu has just dimensions of mass per length times time. Density is mass per length cubed or mass per volume. And then the constant R, gas constant, is length squared divided by time squared times temperature. And then T, capital, the variable T is temperature, so that it has a base dimension of theta. So maybe I'll write this out so it's not too confusing. Mean free path, we know this is viscosity, density, this is our gas constant, and this is temperature. So if we were to write this, we would have to write that length is equal to 1.26 something times our mu is mLT divided by rho, which is m over L cubed, times the square root of our R times T. So that term becomes L squared over T squared theta times theta. And this whole term here is to the power of 1/2. So if we were to simplify this, we would actually get 1.26 in units of length. So it turns out that this equation, because we have units of length on both sides, the constant 1.26 doesn't actually have a dimension associated with it, so it's dimensionless. So we would call this unit now dimensionless. So to kind of bring home the importance of considering your dimension calculations, especially when you get into your careers, there's a large history of major significant engineering problems or case studies. Something went wrong, and a lot of times it comes down to an error in converting units, or forgetting to convert units, or not using the right units. So here's one example, July 23rd, 1983, termed the Gimli glider. Air Canada Flight 143 was a scheduled passenger flight between Montreal and Edmonton, and it ran out of fuel at an altitude of 41,000 feet halfway through its flight. So it successfully was able to land, have an emergency landing in Manitoba. And the reason that they found out for it running out of fuel is that there was calculation error between SI units and British units, and resulted in the aircraft receiving only half the fuel required. So Air Canada's first plane was the first plane to use the metric measurements, and maybe this was someone didn't take extra care in ensuring that the proper amount of fuel was and checking their units. But thankfully, in this case, no one was actually hurt. Another case study, maybe a bit more expensive. In 1999, NASA had the Mars Climate Orbiter crash into a planet. So the Mars Orbiter began its planned orbital insertion maneuver on September 23rd, that time, and it ran out of radio contact 49 seconds earlier than it was supposed to, and they were never able to reestablish this contact. That complications actually came because it actually approached Mars 169 kilometers too close. The diagram below kind of shows the planned trajectory, and the actual trajectory was off by 169 kilometers, which seems like it's quite a bit. And so they think that it was destroyed in the atmosphere, and it didn't re-enter heliocentric space after leaving the Mars atmosphere. And the one piece of ground software supplied by company Lockheed Martin produced results from that piece of software in the US customary units. But the second system, navigation system that was provided by NASA, was anticipating those results to be in SI units. So it was reading US customary units and thinking that they were in SI units and doing calculations based on the wrong units. And they ended up crashing into Mars. Okay, so we have a bit of background in the importance of units. We're going to kind of treat units now as something that basically is back of the hand knowledge, and but always keep in the back of your mind that units are important. We always have to make sure our units are consistent and match. About fluid properties now. What are the units and dimensions, or the quantities, physical quantities about fluids that we use to describe fluids? There's two types of properties. There's extensive and intensive. Extensive properties depend on the total mass of the system, whereas intensive properties are independent of the total, or independent of the amount of fluid. So an example of an extensive property could be mass or weight. Mass of something depends on the total amount of that fluid. So if you have more, the mass is going to change, and therefore the weight's also going to change because weight is associated with mass. And typically, these extensive properties are the dimensions are uppercase, or the units are uppercase. Intensive properties, so these don't depend on the amount of material or fluid that we have. So density, which is rho, pressure, P, doesn't matter where we have a kilogram or a ton of material. Doesn't matter where you go or how much you look at, the density is going to be independent of that. So any property that doesn't matter about how much you have is an intensive property. Extensive depends on mass or how much mass you have, and the intensive doesn't matter how much material you have. Pressure and stress. So if this is our unit volume and we want to do or show a stress analysis or show the components of stress acting on this unit volume, we can divide the stress into two different types of stress: normal stresses and shear stresses. Normal stresses act perpendicular to a face. And so in 3 dimensions, if we have this unit volume, we have a cube with 6 sides in 3 dimensions, and we have a normal stress in the positive direction. We have sigma x, sigma y, and sigma z. These are our normal stresses. And if we draw them at the other sides, they would look like this. So if this is our area of our face, and we were to apply a force on this face, our normal stress would be our force divided by the area. This is probably a little bit easier drawn if we just think about it as one dimension. If we have a bar, and we apply a force on each end, and this is some area, then our normal stress is the force that is acting normal to some surface. So that should be C sigma. Typically, sig will mean normal stress. So this is force, stress acting normal to a surface. Shear stress is represented as the force divided by area, but it is the component of force that's acting along the surface. So if we had a force F here, F, let's call this F normal. Our shear force or our shear stress would be our shear force divided by that same area. And so another way we can write or show our shear stress is if we just have a single unit square. Let's just look in 2 dimensions. Our shear stresses, so something would be in equilibrium, would look something like this. So shear stress is the stress acting parallel to a surface or acting along a surface. So how is pressure related to stress? So pressure, which is defined as lowercase p, is the force acting normal to an area divided by its area. So pressure is normal stress. Pressure is equal to normal stress. So the example over here, this small little diagram shows a unit volume where we have pressure acting on all 5 sides, 4 sides. We have pressure on the left, pressure on the bottom, on the right and on this top angled surface. And if we were to do equilibrium on this, we would find that all of those pressures for this to be in equilibrium have to be equal. And our pressure is equal to differential of force for some small unit over the unit of area. So this is the same definition as normal stress. So you can think of normal stress, pressure, and then another type of stress, hydrostatic stress, which in fluids all mean the same thing. Pressure, normal stress, hydrostatic stress are all the same stress when we're talking about fluid mechanics. Another fluid property that is used in basically all of our calculations as we go through this course, and it's really important, is density. A lot of properties of the fluid are derived by density, and density happens to be a function of pressure and temperature for gases, and mostly just temperature for liquids. We define density as rho, the Greek letter rho, and it's equal to mass per unit volume. So at the side, this little table here, just showing density of air and water at 1 atmosphere in pressure and how that changes at different temperatures. So for the same pressure, we change the temperature, the density of air changes quite significantly, and the density does change, but not as significantly as air. So because liquids vary so little with pressure, we call liquids incompressible. But it does vary with temperature, so we do have to consider differences in density at different temperatures. So for example, at 4 degrees C, water is at its most dense. It is 1,000 kilograms per meter cubed, but water at 100 degrees C, right before boiling, is equal to 958 kilograms per meter cubed. So the density decreases as we increase temperature. If the temperature range over a problem that we're solving is pretty small, then we can usually neglect the pressure or the density change due to temperature. Gases, on the other hand, we have to consider temperature and pressure because these are compressible. An amount of pressure can significantly change the density, and then likewise, so does temperature. So we have to consider both temperature and pressure when we're dealing with gases. Another fluid property is specific weight. So density was mass per unit volume. Specific weight is the weight per fluid volume. And we can write this in terms of density if we think of the relationship between weight and density. We can write this as specific weight to our density, which we also can call specific mass, times gravity. Density and acceleration due to gravity. So you will usually not see specific weight written in the top form. You'll almost always see it written in this form down here. Another measure is something called specific gravity. So this can be sometimes confused with specific weight, but specific gravity is defined as the ratio of the density of a substance with respect to the density of water. So whenever we talk about specific gravity, we're just relating how dense something is relative to water. So a specific density that is above 1 is something that is more dense than water. Specific density of 1 is things that are around the same density as water, and less than 1 means that we have something that is less dense than water. So the table at the side here shows some examples of that. Gold, uranium, mercury, very heavy, very dense metals have a specific gravity between 10 and 20. And then as we get to the other end of the spectrum, we have petroleum, plastics, and even some really light woods like balsa wood can have a specific gravity of 0.17, 0.72, and so on. Next fluid property, this has to do with a measure of resistance to change in volume under an applied pressure. And we call this bulk modulus. And this property comes into play in solid mechanics as well as fluid mechanics, especially when we were talking about things like speed of sound in a medium. We see bulk modulus pop up. So if it's the resistance to change in volume under an applied pressure, and it's a modulus, we could think of it as the slope of the pressure versus volume change. So if we rearrange this, we could see that a change in pressure dP is equal to negative bulk modulus times our dV over V. Well, this is our volumetric strain. So if we think back to our mechanics, this is very similar to a Young's modulus type equation, where we're applying pressure or stress. Pressure, think of pressure as normal stress. It's equal to some constant bulk modulus times our volumetric strain. So materials with a high bulk modulus are really, really resistant to volume changes under applied pressure, and materials with a low bulk modulus are not very resistant to a volume change when you apply pressure. So liquids, for example, have, in general, a high bulk modulus, and gases have a low bulk modulus. So you don't need to apply much pressure to change the volume of a gas, but you have to apply a huge amount of pressure to change the volume of a liquid. And that's partially the reason that we call liquids incompressible. So where this shows up, like I said, is in the calculations for speed of sound. The speed of sound C is related to the bulk modulus of elasticity. So what this is, the speed of sound is essentially a pressure wave traveling through a medium. If a material resists a change in volume due to pressure more, that means it's going to be able to transmit a wave a lot faster. And then likewise, if a material is really, really heavy, the inertia of that material is going to slow down the transmission of that wave. So the speed of sound is related to, or is equal to, the square root of the bulk modulus divided by the density of the material. So if we have a really, really stiff, high bulk modulus material with very low density, we can have a very high speed of sound through that material. Whereas if we have a very spongy, low bulk modulus material that maybe is very, very heavy, we'd have a very, very slow speed of sound. So just to compare two common mediums, fluids, air and water, the speed of sound in air is about 340 meters per second at standard temperature and pressure. And for water at 15 degrees, the speed of sound is about 1,450 meters per second. So as important as density, I would say, and pressure is the property of temperature. Temperature, maybe some debate over what it actually means, but temperature is a measure of the internal energy of matter. And in the case of this course, we're talking about fluids. And we can measure the internal energy in different scales. There is the relative temperature scale and the absolute temperature scale. Almost all calculations when talking about thermodynamics are in the absolute temperature scale, which is either Rankine or Kelvin, depending on which unit system you want to use, either English or SI units. But for the most case, we'll probably be dealing with Celsius and Kelvin in this course. So absolute just means that the temperature goes down to zero absolute temperature. 0 Kelvin or 0 Rankine is the lowest temperature. We theoretically can't go any colder than that. So that is the moment at which all of the internal energy of matter is gone. We cannot take away more internal energy when something doesn't have any energy to take away. So that is absolute 0. and the temperature increases from there. Celsius is relative because we have that temperature scale relative to the properties of water. 0 degrees Celsius is when pure water freezes, and 100 degrees Celsius is when pure water boils, and we've developed a scale around that because that's the most common fluid that is involved in much of our lives. So that's it. That system is quite simple to use. And 1 Kelvin, I guess to complete this, 1 Kelvin is equal to, or a degree Kelvin is equal to a degree Celsius plus 273.16. And likewise, for Rankine, 1 degree change in Rankine is equal to degree Fahrenheit plus 459.69. So a degree change in Celsius is the same as a degree change in Kelvin. They're the same, I guess, magnitudes. Each degree change is the same magnitude in Celsius and Kelvin, and Fahrenheit and Rankine, each degree change is the same magnitude. And they're just offset by 273 degrees for Kelvin and 460 degrees for Rankine. So those are a lot of the base fundamental properties. Now we're starting to get into some properties that are a little bit more abstract. So in fluids, probably one of the most common types of properties that you will see or hear is called viscosity or dynamic viscosity. Usually we just call it viscosity, but it is dynamic viscosity, and we'll see how that's different than something called kinematic viscosity later on. So in fluids, we said that they can't resist shear forces, but if you were to go water skiing, the water is pushing back at you. There is some force of resistance. So it's not entirely true to say it does not resist shear forces, but what actually happens is the fluid deformation under shear is represented by continuous movement, and it is the rate at which the fluid is shearing or deforming is what gives us this resistance force. And that resistance force is related to the property of viscosity. Materials that are very low viscosity tend to deform and flow quite easily, and materials that have very high viscosity have a lot of resistance to flow. So if we wanted to think about what actually gives rise to this, think about viscosity being related to how sticky the atoms are together in a fluid. If we have this top plate on the bottom left here, we apply a force to the top plate, F, and all of the fluid underneath is going to be shearing. The top fluid is going to be moving at the same speed as that top plate, and the speed will slow down as it gets closer and closer to that bottom plate. But why is it actually resisting? What's causing that resisting force if it can't resist shear stresses? Well, if we look at the individual molecules, the ones at the bottom are going to be moving slowly, and the ones at the top are going to be moving faster. As these molecules can flow freely and mix, the momentum of the slow-moving molecules is going to slow down the fast-moving molecules as they mix and or come into contact with each other. And there's a principle which we'll call later, or we'll see later, called the no-slip principle, which means that any fluid that is right at the adjacent to a boundary has to be moving at the same speed as that boundary. So the molecules at the top, if they want to slow down, that means they're going to resist the motion of that top plate, and it'll appear to be like some sort of drag or some force resisting the force applied to that top plate. So that's all related to the property of viscosity. So many years ago, Newton, if you know from our dynamics courses, came up with this law of viscosity. And he said that the shear stress applied to a fluid is proportional to the velocity gradient. So what does that mean? If we look at the top figure here, we're applying a force that is parallel to the that plate. So the force is acting parallel to the face that that fluid is acting on. So it is a shear force or shear load. And as we pull that and the top plate starts to move, we're going to create something called a velocity gradient. Velocity gradient is just a change in velocity with respect to a spatial dimension. So as we move around in space, so if we move around in the y direction, the velocity of our fluid is going to be different. So Newton said that the amount of shear stress that that fluid is going to push back on that top plate, or that we're going to exert with the plate onto the fluid, is proportional to the property of viscosity times that velocity gradient. Simply think of the shear stress in a fluid is not related to the deformation, it's related to the rate of deformation, how fast. So U is velocity. So we'll say rate of change of fluid velocity with respect to distance y. And y is just a direction perpendicular from whatever plane or face that we're calculating the shear stress on.
Would you be able to explain the du again?
So if we look at a differential volume element and we say the shear stress is equal to the differential of that small force divided by our differential area, we take the limit for an infinitesimally small differential volume, we get shear stress is dF over dA. And we have a definition now for shear stress, but we want to figure out what is the definition for shear strain. So a measure of strain is basically the angle that's formed by a deformed or a deforming volume element. So if you look at the figure at the bottom here, we have this square, and we're applying shear stress loading to top and bottom surfaces. And the definition of shear stress is this delta x divided by the dimension delta y. So our shear stress just becomes delta alpha is equal to delta x over delta y. This is how we would define the shear strain for a solid, where delta x is some displacement in the x direction, but in a fluid, the shear strain, using it as a displacement, is not really a good measure because the shear stress isn't related to displacement, it's related to velocity. So that delta x term, we have to actually take the time rate of change consideration for it. So if we take delta A down here and we divide it by delta T, right beside delta alpha divided by delta T is equal to delta X over delta Y over delta T. Which we can just say as delta X over delta T times 1 over delta Y. And a change in X with respect to time, that's the actual dimension that's changing as we apply our shear stress. This is just equal to our velocity U, or delta U. So that we can just write our shear strain divided by time with respect to time is equal to our velocity gradient, or if we write it in differential form, dA dt is equal to du dy. So if we put all this together, we know that Newton postulated that, okay, our shear stress is proportional to our velocity gradient. There must be some proportionality constant, and we'll call that proportionality constant viscosity. And we end up with the shear, Newton's law of viscosity. So at least remember this equation right here. So the shear stress at a point y away from is equal to the dynamic viscosity mu times the velocity gradient at that point. And if we look at this a little bit closer, we wanted to make sure it's dimensionally consistent. We see that mu actually has dimensions of stress time. So mu has dimensions in SI of newtons times seconds per meter squared, or if we look at the British units, pound per second, or pounds times second divided by foot squared. So this on the right-hand side would just be a typical or an example velocity profile. We call this a velocity profile. And a velocity profile just shows the velocity u as a function of y, which is just this distance from some wall, some surface. And anytime you have a fluid in contact with a wall, the fluid must be moving at the same speed as the wall. So v wall is equal to u when y is equal to 0, and vice versa. So that's called our no-slip condition. So the speed of the fluid in contact with the wall has to be going the same speed as the wall. If the wall is stationary, that means the fluid is stationary. If the wall is moving, that means the fluid is moving and at the same speed that the wall is moving. So we've probably heard before about Newtonian fluids and non-Newtonian fluids. So Newtonian fluids are basically any fluid that follows the Newton's law of viscosity. So this equation up here. If we have this equation holds true for a fluid, then it is a Newtonian fluid. And we can look at if we plot the shear stress versus the velocity gradient of different kinds of fluids, we can see that as the velocity gradient changes, the shear stress changes proportionally. So that proportionality constant is our viscosity. And depending on the slope of this curve, we have different viscosities for different materials. And here's a table of some viscosities for different materials. So hydrogen has a viscosity of 9 times 10 to the minus 6 kilograms per meter second. And to the right of this, we have just the ratio of the viscosity relative to that of hydrogen. So water has a viscosity 114 times greater than hydrogen. It's equal to about 1 times 10 to the minus 3. And then a really viscous material is glycerin, viscosity around 1.5 kilograms per meter second. Non-Newtonian fluids behave unlike Newtonian fluids in that they don't follow Newton's law of viscosity. They obey some other law. So they do not obey Newton's law of viscosity. And a lot of times non-Newtonian fluids can be expressed by this equation right here. So instead of having mu as our proportionality constant, we have some other constant k called the consistency index. And then we raise the velocity gradient to the power of n, which is called the power law index. So in the special case where a fluid has a power law index n equals 1 and a consistency index k is equal to the viscosity mu, then the material or that equation reduces to Newton's law of viscosity and we have a Newtonian fluid. So any other case where n is not equal 1 and k is not equal mu, we have a non-Newtonian fluid. And if we play around with this equation a bit, what we can do is we can factor out one multiple of that velocity gradient, and we get this term out here. And we call this our apparent viscosity. So our apparent viscosity now basically is a function of our velocity gradient. So if we have fluid moving faster or slower, our viscosity changes. And that is a non-Newtonian fluid, where the viscosity or the apparent viscosity depends on the velocity gradient of that fluid. And we've kind of classified non-Newtonian fluids into different types of fluids. There's Bingham plastics, which actually can support a shear stress before it flows. And then we have shear thinning fluids and shear thickening fluids. So this graph here is just the same as before, where we'd have tau and du, dy. So we're not going to deal too much with non-Newtonian fluids in this course. Most of the fluids we're dealing with are water and air, and they are Newtonian fluids. They behave like Newtonian fluids. Important to think of how does temperature and pressure affect the behavior of these fluids, especially viscosity. So we talked about how temperature and pressure affects things like density, and that also affects our property of viscosity. So in general, increasing the temperature will decrease the viscosity in liquids. So higher temperature, lower viscosity means easier flow, less resistance to flow as we increase temperature in liquids. Whereas in gases, if we increase the temperature, we get an increase in viscosity. So if we have higher temperature gases, we have resistance to flow. The viscosity increases only slightly in liquids, though. It's not too much. With increasing pressure, whereas the change in pressure for gases is a little bit more. So typically we ignore the viscosity effects of pressure, and we only really consider the effects of viscosity and temperature. And this chart at the side just sort of shows the absolute viscosity for different materials at different temperatures. So we have our gases don't really change with temperature too much, but our liquid change quite a bit more, as those molecules are a lot closer together, so changes in temperature affect how they interact because they're so much closer to each other. So here are just some, I didn't need to spend too much time on these equations, but these are just some empirical equations that are based on numerical data for determining your viscosity as a function of temperature. So there's Andrade's equation and White's equation for liquids, and there's Sutherland and Power law equation for gases. So if you have your viscosity at some reference temperature, mu0, you can calculate your viscosity at another temperature, T, and all you have to do is look up in a table what those constants A, B, C, E, and so on are for different materials. So we kind of hinted before at kinematic viscosity. So everything we've talked about so far is called dynamic viscosity, which we'll just call viscosity. Another way to represent viscosity is kinematic viscosity. And kinematic viscosity is just essentially taking your viscosity, your dynamic viscosity, and dividing it by your density. And it's called kinematic because it suddenly, it's dependent on your mass or your inertia. So it has an inertial term. So your kinematic viscosity, which is the Greek variable nu, is just defined as your dynamic viscosity mu divided by your density rho. Another term that we're going to see throughout this course is the concept of inviscid versus ideal fluids or viscous fluids. An inviscid fluid is a fluid that has zero viscosity. So that means that mu is just equal to 0. And most of the time, we would love to work with viscosities that are close to 0 because that means that there's very low resistance to flow, which is very good for things like lubricants or any cases where we don't want to have to really consider the shear stresses acting on a fluid or a flow because it just adds complication to it. So a lot of times we can assume that the viscosity or the viscous forces are low enough that we can say our flow or our fluid is even though it's not, it's close enough that we can say it's basically inviscid. So for example, the viscosity at 20 degrees C of water is around 10 to the minus 3, whereas the viscosity of air is 18 times 10 to the minus 6. So depending on the situation, we could assume that if the magnitude of these are low enough, which means that our shear stresses in the situation are low enough, maybe compared to other kinds of stresses, then we could just ignore it and we can say the fluid's inviscid. But ideally, in the real world, fluids are both, in the real world, fluids are not inviscid, but if we have a special condition where we say our fluid is ideal, that means inviscid and incompressible. So if we were to look at water, which is a liquid, and we consider that incompressible, and we ignore the viscous effects, or it's close enough to zero, or it doesn't really change our equations, then we can say that it is ideal, which means it's inviscid and incompressible. Don't worry about how the equations above are derived. I'm not going to test you about how to derive these equations. All of the testing and practice problem assignments will be on actually using these equations. I just want to go over today sort of the concept of how they're come up with, how they were determined, but I'm not going to ask you to derive these equations. So let's do an example. So it's a lot of material to take in. So let's just start with a simple viscosity example where we have a velocity gradient that is linear. So that means the slope of our function of our displacement or our velocity with respect to distance y is constant. So for this example, we say suppose that the fluid is being sheared as shown. We'll say the fluid is SA30 oil at 20 degrees C. Compute the shear stress if the oil, if the velocity v of the top plate is moving at 2 meters per second and it is 2 centimeters above the bottom fixed plate. So how would we go about solving this problem? What are some assumptions we're going to make? Right, no slip. So no slip condition. So we're going to assume that the velocity, so that means u at 0 equal to 0, and the velocity at the height h, which is 2 centimeters, is going to be equal to v. So if we have those assumptions, we can assume a velocity profile. If we do one more thing, which is assuming that figure shows that the function uy is linear. So our approach is basically find du dy, and then from this calculate our shear stress. So what are our property values? We need to know u, and for SAE oil, if we go back to our equation above, our table above, where's our viscosity for SAE oil, 0.29 kilograms per meters seconds. .29 grams per meters seconds. So our solution steps, how do we find our velocity gradient? How do we find du dy? there any thoughts on how we would find that? Yeah, one suggestion is V over H. So we can say du dy is equal to just the slope of that line. And since the line is linear, it's a straight line, we can just say that's equal to delta u over delta y. So we have v minus 0 over h minus 0 is equal to v over h. And we know the value of v is 2 and h is 2. So this simplifies to what? Can we just calculate this directly? Is it equal to 1? Right, good. It needs to be in meters. So we have our velocity at the top is in meters per second. And our height is given in centimeters. So our height is not equal to 2. You can write this as equal to 0.022 meters per second divided by 0.02 meters. Gives us 100. Now the units of 1 per second. So we're not confusing that 1 as another unit. We'll just call this seconds to the minus 1. So that is our velocity gradient, or we can call it our shear strain rate. We think of shear strain is unitless, and a shear strain rate is our unit of strain divided by with respect to time. So it should be seconds to the power of 1 over 2. Finally, we have to find our shear stress, which is multiply that by mu. Mu is 0.29. Kind of running out of space. Is this the same question? This is the same question, but it's right over here. So tau is just mu times value 0.29 times 100, which is equal to 29 pascals. So this example here is a different answer because I think copied the plate wrong and is supposed to be moving at 3 meters per second. Yeah. So we'll ignore this. We'll go with this result up here. So all we did here was we were given a velocity profile. We were given some information about the boundaries at the plates and the distance apart. We assumed it's a linear. We assumed it's Newtonian fluid. So we found the velocity gradient. We looked up our value of properties we need, and we used the Newton's equation for viscosity. So let's look at a slightly different problem. In this example, we have an oil film with a viscosity mu and a thickness h, which is much less than the radius of that disk. So we basically have a spinning disk, and it's resting on top of a oil film on top of a fixed wall. So the disk is rotated steadily with an angular velocity of omega. And if we note that both the velocity and shear stress vary with the radius, derive a formula for the torque, capital M, required to rotate the disk. And we're going to just ignore air friction or air drag. We're just going to consider drag due to the rotating or the fluid motion underneath that rotating disk. So what are some assumptions that we would need to come up with for this problem? The first one could be that we have a linear velocity profile. If the spacing, like in our previous example, that did small, usually you can get away with assuming that you have a linear velocity profile unless it's told to you otherwise. It's a pretty safe assumption for a really small. We'll also assume it's Newtonian. So our approach is basically we need to estimate the shear stress on a circular strip as shown in figure B. So estimate our shear stress for a strip. And we would have to integrate over the entire area of the disk. And their property values are basically just going to be mu of the oil. We don't have any of their properties that are really considered. There's no temperature. So yeah, maybe just some more explanation on this figure. So what's happening is we have this disk here. This is, say, a handle or a shaft that goes and connects to a cylinder, a disk. And then this view on figure B is like if we imagine this is our pupil looking down on that disk. So this is the top. And we have our circular shaft. We're imagining just looking at the disk now, we have a differential elements that we're going to do analysis on, which is this gray ring. And the fluid is between the disk and the wall. So basically that fluid's just acting as, you can imagine it as a lubricant between a fixed wall and a rotating disk. And we're just trying to calculate what's the moment that you need to generate to cause the disk to rotate at a velocity omega. We have to assume that we have a linear velocity profile and we have a Newtonian fluid and property of oil. So the property value, what is the property of oil? Did it say what kind of oil it was? I guess it's just going to be solved in terms of variables, so we don't need to actually find the properties. The only property value that we're going to use is mu. So basically what we're going to have to do is at a radius r, the velocity in oil is tangent to the motion of the disk. So if we were to try to draw a zoomed in section of the disk, let's assume this is the oil in between and then it's sitting on top of our plate. If we to draw the velocity profile, say this is spinning this way. A point right here would have a velocity v, and that might be a function of r. Let's not use v, let's be consistent, let's use u. which is going to change as a function of r in this direction. And then we're also going to have u change as a function of y. So basically, we can find the velocity at the top of the plate, which is going to be u as a function of r. Find the velocity in the fluid as a function of that rotating disk velocity. With this, essentially, we're going to have the of the disk is going to equal u is equal to omega times r. So the further we are out, the tangential velocity u is just going to be equal to that rotational velocity times the distance r. And then the gradient is going to be this velocity divided by h. So we get, using our Newton's equation, our shear stress is going to be equal to mu times omega r over h. And then so we take the moment is just taking that shear stress and then integrating it over the area of that disk. I think I just froze up for a second. So the area of that disk, if we just look at a differential disk, is 2 pi r times dr. So the differential moment acting on that small disk, dm, is our shear stress times the area, dA, and then that's the force times the distance away, r. So we get our differential equation here, dm is equal to tau dA times r. We have an expression for tau, our shear stress. So if we substitute that in, we get this equation here. Or this is our shear stress. So we have a function dm as a function of r and dr. And if we take out all of those constants, our 2 pi mu isn't changing, omega isn't changing, and h isn't changing with respect to r. And we integrate both sides. We get our moment m is equal to the integral of 0 to the outer radius of r cubed. So we get our final answer as the total moment of resistance based on the property of viscosity mu is equal to pi times mu times whatever velocity we want, omega, times the radius of the disk to the power of 4 divided by 2 times h. So this is a little bit more complex problem just because of the geometry, but you can see how quickly a simple problem from before, we had a plate moving boundary, just applied it to a rotating disk now, and the equation or the calculation gets significantly more difficult quite rapidly. So make sure, I would say, understand this example, and if you can understand this example and how it's solved, you go through it again later on and see if you derive the same equation on your own. The last or second last topic I wanted to cover today is surface tension and capillarity. This is an important fluid property, specifically with liquids. So there's two, I guess, that happens due to forces acting between liquid particles. And so if molecules of a liquid are attracted to one another by a force, we tend to call this cohesion. So cohesive forces are liquid molecules pulling each other together. And when liquid molecules attract molecules that make up a container or some other material, we call that adhesion. So why do we care about cohesion and adhesion? Well, because molecules of liquids have these properties of cohesion adhesion, which just means that the liquid molecules, they want to stick together more or less than they want to stick to other materials. You can get some interesting properties, and they kind of manifest in what we call something called surface tension and capillarity. So surface tension is essentially an apparent force that acts on the surface of a liquid interfacing with something else, whether that interfaces with a solid or a liquid. And these give rise to things like bubbles or meniscus. When we're looking in chemistry class and we're measuring different amounts of fluid, we have to consider the meniscus, and that's due to adhesion, the fluid wanting to climb up the sidewalls of a glass. So why does surface tension actually behave the way that it does? Why doesn't the fluid just, break apart? Why is the surface tension so strong that we need to actually call it something? So if we imagine a fluid, a liquid sitting in a container, every molecule is being attracted by the molecules around it. And the molecules that are near the surface, so near the surface here, only have molecules below that are attracting it. So there's a net force downwards wanting to pull those molecules back towards all the other liquid molecules. And there's no force pulling them up off the surface. And that difference, that net force downwards, is actually enough that we can see fluids and liquids behave in different ways depending on the strength of this bonds between these atoms. So one of these phenomena is actually water droplets. Water droplets form because of surface tension, and they form into little spheres because a spherical shape minimizes the energy of a system, or what we call the free surface energy, or the work per increase in surface area of the liquid. So it can contain the most liquid with the least of the surface. So if we wanted to calculate the pressure inside of a water droplet, we could actually do that. And how would we do that? Delta P, pressure inside a water droplet. If this is our unit, and we just did a force balance. So we're looking at this half of a water droplet here, and we're just going to do an internal stress analysis or force balance equilibrium. What we would have is our pressure, or let's say start even before some of the forces. Let's just arbitrarily say this is the x direction. Some of the forces in x must be equal to 0. And so the forces in x would be the force due to our pressure difference, pi times r squared is the area times our pressure gives us our force. And then if we subtract in the other direction the force of the surface tension, which is parameter gamma, so we have 2 pi r times our surface tension. This must be equal to 0. We can get the difference in pressure for a water droplet. So that's the difference between the pressure inside the water droplet and the outside of the water droplet, just due to surface tension, is equal to 2 times gamma divided by R. And if we did the same analysis for a bubble, the difference between a bubble and a droplet is that a bubble would now have two surfaces on the inside and outside. So essentially the pressure difference is twice as much as a droplet. So we can write pressure for a bubble is equal to 4 gamma over R. So how we derive this is just basically doing a force balance. If we look at the force acting on due to surface tension, and we do some of the forces, add them to 0 and rearrange, we can get our delta P's. And delta P here is just equal to P minus PA. And PA is just the atmospheric pressure. So yeah, here it is just summarized again. So here it's just use sigma. I can't remember which version your textbook uses. I think your textbook uses gamma. I just know it's the surface tension. So for a more general surface, if we have a cylinder, the pressure difference between the cylinder, our surface tension sigma over R. And for just a general plane surface, it is sigma times the average of the inverse, or some of the inverse of the radiuses of your curved surface. So the capillarity is a property where our material has cohesion competing with each other. So in the case of a water droplet, you might just have a water droplet free in air, or we're not really considering the effect of it acting on a liquid or a solid. But when we have capillarity, capillarity is when adhesion is either stronger or weaker than cohesion, affects the liquid and solid interface. So if we have a case where adhesion is strong, cohesion, then I think I have this actually backwards. If we have adhesion stronger than cohesion, I'm going to fix this before I upload it, but this is backwards. Liquid wants to adhere or stick to or cling to another material more than itself. It is something that we would call good wetting property. Or you would see behaviors like this, where the material is sort of climbing along a solid surface. If we have cohesion, so the material wants to stick to itself stronger than something else, we have something called a non-wetting material. So this would be an example of non-wetting materials usually would form droplets on a surface. And a good example of a non-wetting material would be like mercury in glass. Mercury does not want to adhere to glass at all. It wants to stick to itself much more. So it would look more like the left. So this would be mercury in glass. And this, a good wetting material would be water and glass. So basically, we have wetting and non-wetting materials. Wetting materials really want to stick to some surface. Non-wetting materials really don't want to stick to some surface. Because water generally has really strong adhesion, it wants to stick to a lot of different things. We can sometimes apply coatings to reduce that adhesion effect. So if you had a water droplet, for example, and it would have a lot of adhesion strength, a water droplet might look like this. And it wants to wet with that surface. And if we wanted to reduce that effect, maybe we wanted to, I don't know, reduce the, we wanted to make a material that was hydrophobic. What we could do is we could coat this in maybe an oil or some other kind of material that has a low adhesion with water. And so this could be, the blue could be water on glass. And then the red could be, for example, water on oil. So it's not really dependent on just the liquid itself. It depends on the interaction of the liquid and the solid it's interfacing with. So just because water has good adhesion with one material doesn't mean it's good adhesion with other materials. Another way that you can see this is if you were to drop oil into water, they really don't want to stick together, so the oil will form droplets in the water, and then vice versa. If you have a small amount of water and oil, it'll form small little droplets. They just don't want to stick together. They want to stick to themselves much more. So we can add things like soap or other materials, other things like soap that would try to break up these behaviors so that those things can mix better, and you can increase something called wettability. So we'll just do a quick example with capillarity, and I think we're pretty much done for today. So this question says, derive an expression for the change in height in a circular tube of fluid with surface tension sigma and contact angle theta. So basically what's happening here is you have a column or a tube that's placed in fluid, and just because of adhesion, that fluid starts to climb up that tube. And so you're going to have a balance of forces. You're going to have the weight of that fluid column pulling the fluid back down, and you're going to have that fighting against the surface tension forces trying to pull that fluid up. So we're trying to figure out what is that force balance equation, and how can we solve for the height of that liquid that's in that tube. So if we look at the force going up, due to surface tension would be equal to the stress sigma, the component of that that's vertical. So that would be some angle theta, which is a contact angle, which is a property that's given to us. So that would be equal to cos theta. And then the total force would be multiplying that by the total circumference of that tube. And the total circumference of that tube, if we know the diameter of that tube, let's say that is 2r, then that would be equal to r squared. So that's the force due to sigma. And then the down that's pulling it back down is our weight, and that's equal to the volume of fluid, or the mass of the fluid times the acceleration due to gravity. And so we can write that as equal to, who knows? What is that force down? What is the weight of a column? Yeah, rho times the volume times gravity. Whoops. So rho, the volume is area pi r squared times acceleration due to gravity. So if we equate these, they're zero. The sum of the forces is equal to 0. That means the force up is going to equal the force down. And we rearrange this, we get sigma cos theta pi r squared is equal to rho pi r squared hg. And then we're asked to find that height. So we can isolate this and we get height is equal to our pi r squared terms cancel out, and we get sigma cos theta divided by rho g. So suppose r is equal to 1 millimeter. I think I made a mistake here. I used area for sigma. This shouldn't be area. This should be 2 pi. So that surface tension sigma is a unit of force per unit length. And so if we multiply that by the circumference, that gives us the total force along the length, that is the circumference. The circumference is 2 pi r. So we don't have both r's cancel out. We still have one r and a 2. So how does this rearrange now? We have h is equal to sigma cos theta times 2 over r. So then if we solve the question below, suppose that our value of r is 1 millimeter. Calculate the capillary rise for water, air, glass. It is equal to 0. So it has a really strong wetting, really strong adhesion. Our surface tension is 0.073 newtons per meter. And the density is 1,000 kilograms per meter cubed. So if we solve this, see if you guys can get the same answer, which would be equal to 2 times 0.48, 0.073, sorry. Times cosine 0, which is just 1, divided by 1,000. Divided by 9.81. Divided by r is just 1 millimeter or 0.001. We should get anyone have a calculator handy? Here we go. 0.015 is an answer. And our units H, we canceled everything out and we used the correct units. This should be in meters. Good. So water, forces wants to climb up a tube so much that if the tube was 1 millimeter in radius of 1 millimeter, and it had these properties, it would climb up that tube about 0.015 millimeters. There will be an importance of significant figures in the class for your quizzes, but I'll make those very explicit. These examples I'm showing in the class, I'll try to follow significant figures as best I can. For example, right here, radius of r is equal to 1 millimeter. If we convert that to meters, then I guess it's 3 significant figures. So this would be 0.001 meters, or 1 times 10 to the minus 3. I mean, it's not still 3 significant figures. The answer we give here should just be to 1 significant digit. I will try to make sure from now on, the next lectures, we do more examples, that always be considering significant figures. So yes, do consider significant figures. My recommendation for dealing with significant figures is to, through relations, carry as many digits as reasonable. And then when you're giving your final answer, that's when you do your rounding. So don't round anything for your intermediate calculations, just round your final to whatever significant figures would need to be. So that's where we'll finish off today. We'll just do the last 2 slides, ideal gas law, next week. And I know this week was long. I'm sorry for putting you through a long bunch of lecture slides. Future materials will be much more going through example problems, and there won't be as many slides to go through. I'm not going to try and bore you sitting here all the time listening to lecture slides and lecture presentations. I don't like doing that, and I know you don't like sitting through that. So I promise this will be the last one, but I do recommend getting a copy of the textbook one way or another so that you can read the textbook as we go through.